We sell a derivative of machine learning software. And I'm really appreciative to Matt for allowing me to speak today, because I asked him to do that because I have a message that I wanted to deliver to the leaders of the data-driven movement in New York. And that is that we've hit a new phase in the capabilities of the technology that is being sold. And so this presentation is designed to appeal to both technical and non-technical people. But the message here is that the new generation of software is automated and can do things that data scientists used to have to do by hand. And the reason that this is powerful and disruptive is that the industry has been telling you for a long time that the lack of data scientists will prohibit industries from taking advantage of data and making money from it. And as automation becomes available in the market, industries will get disrupted. And we're seeing this right now in finance, actually, with the deployment of our product, which is why we've opened an office in New York. And so what I'm going to show you today is an actual demonstration that looks at a problem that is more than 2,000 years old. And the problem required the greatest mind of its generation, a guy named Hero, who was a professor at Alexandria, to solve without big data tools. In fact, he used just basic algebra. Hero, our technology represents a shift, because today, for the first time in public, we're going to show you that the tool can automatically derive a formula that it took Hero several years to build, and literally his creative genius to figure out how to do. And now our software does this automatically from data in a few seconds. And so the power here is that when people who are data scientists approach problems, they essentially do the same thing that Hero did. They sit down and they're expected to use the creative process to figure out exactly how to produce an equation or a set of equations that allows them to learn whatever it is that they need to know about a market or about advertising or about anything, so that they can profit from it. And that process typically takes a long time today. And if you can automate it, you can parallelize it, and you can accelerate it. And you can cut the time to market for making these decisions and profiting from them. So we call that a new phase in big data. It's Big Data 2.0. Big Data 1.0 was enabling heroes, people like Hero, to have tools to allow them to use their creative genius. Big Data 2.0 is about automation and bringing that to many more people. So let's look at the problem. And this is very much a small data problem. It's got 3 input parameters: the sides of a triangle. What is the area of the sides of a triangle? In 50 AD, they didn't know. They didn't know the general equation. And again, a small data problem, there are only 3 sides. What could the area be? And the ways that they actually computed the area of a triangle back then would seem crazy to the rest of us. I mean, most of us know the equation is 1/2 base times height, and you can compute it from in a variety of different manners. But when Hero did this, it was really in a revolution. And so the question is, how do you take this problem, this small data problem, and convert it into a big data problem that a machine learning system can solve in an automated fashion? And so today, I mean, literally in a few minutes, I'm going to do this for you and walk you through the steps. And I assure you, regardless of how technical you are, you can understand this. It essentially involves 3 steps. The first step is you give the software a lot of triangles. You give it a lot of examples. And in this case, we're going to do 100 million examples. And some of them are going to be misformed triangles. Some of them are going to be triangles that are not actual triangles. So we're going to give it the lengths of the sides, and not all of the side lengths will actually be valid. Okay? And then step 2, we're going to run this little script, and that's literally how long the script is, 2, 4, 6, 7 lines in our product. That's Python for those of you who are interested. And then it's going to output that equation. Now let's see if this actually works. All right. It's doing something. All right. So it started. So actually a little bit of information. Oh, great. Okay. So hopefully you can read this. I'm going to actually put this here so it's more in the center of the screen. No, that didn't work. All right, I'll hold it there. So this, I just started it. And what this is going to do is start up 120 servers to analyze the 100 million triangles to figure out what the generalizing equation is for calculating the area. We'll come back to this in a second. So let's talk about what the input looks like. It's exactly what it seems like. It's just a big block of triangles. And people over here, you'll have to look over to the other ones. But it's just a big block of triangles with the side lengths. And one of the reasons that we are looking at triangles that are invalid is because it simulates what happens in the real world. You know, people get really noisy data for a variety of different reasons. And there's no reason to expect that great data will come into any problem that you work on. And so just to quickly walk you through this script, the first line in the script imports our libraries into Python. The second line imports an app that wraps around, it basically establishes an app that we call Triangle. The third line initializes this app. And then we jump down into the fourth line, which is generating 100 million triangles. And this particular function has just been defined to generate the 3 sides, and some of them have areas. And then the fourth line, which is right around here, basically does all the work. And it says, go out and build me a model that represents the generalization to find the area of a triangle. And this particular line of code is what causes the 120 servers to go off and go to work on this thing, building models, testing different ways to parameterize the models to see which one is most effective at estimating the answer. And obviously it's doing a lot of work. And then the bottom 2 lines are just scoring the output and generating some diagnostic information. Okay, so this is really hard. I'm not kidding. The technology that's gone into this, myself and a bunch of the other people on our team have worked on for literally 14 years. This is incredibly hard because the number of possible parameters and model combinations is incredibly large. This is an NP-complete problem. And the question is, how do you attack it? And so our team has done, from a process perspective, you look at different ways to transform the input variables, and we'll talk about that in a minute. You look at other different ways to transform the problem to make it tractable. And to do this, our team has built an incredibly high-performance system for analyzing models. So our team has essentially 2 groups. One, which is the high-performance computing group, which as the leader of that team came from Bing, where he was the architect for what's called the Cosmos system, which is the engine that runs all of Bing and also Microsoft's ad network. And then other members of the team came from Google's distributed systems team. And together, they're working at my company to build the next generation of high-performance systems to do analysis. And then another part of our company is the data science group, which has optimized a pipeline to run on top of that infrastructure such that you can do analysis of millions of models in the time that it takes most companies to frankly do one. And when you couple those things together, you have an incredibly powerful system for automating what people have been doing by hand for years. And so let's talk about what they're doing by hand. They're trying to figure out how to transform the original 3 input variables, side lengths A, B, and C, into something that makes sense to the computer, to the machine learning algorithm, to the statistical evaluator, et cetera. And I have some examples of that. So if you're Hero in 50 AD, you did some basic mathematics. You took the equation and you started to play with it with a bunch of mathematical transforms. And you'll notice that all of the equations have similarities in the sense that they end up as polynomials. And machine learning systems are actually really good at finding the coefficients for polynomials when the problem is structured well. And so given this kind of formulation, the question is, how does a system automatically build the polynomials? And so again, if you're a data scientist, that's a little off, but if you're a data scientist, what the data scientists are doing today is essentially trying, through trial and error, to come up with the right set of numbers that can be plugged into this polynomial equation to generate an answer. And so this is actually a valid answer to the question, but it has error. You know, it has about 6% error on the set that we were working with. You know, the last time I ran it, it can vary based on random factors, but it's about 6%. And what we're doing here is we're giving the machine learning system side lengths A, B, and C, and then additional numbers, which are A times B, and A times C, and B times C. And you'll notice, if we go back a few slides, that actually looks very similar to this equation in the system. It's very similar. It's not quite the same, but it's very similar. And because of that, the system will actually get a fairly good answer. It's good enough, in fact, that if you were a data scientist working at LinkedIn or on Bing, you might stop. You know, you can make money with a 90% answer, you know, especially on problems where there's a large data volume. But if you're working on scientific research, this might not be good enough. You know, if you're trying to predict whether someone might die from a disease, this might not be good enough. And so you can do better. And another way to parameterize the equation is just to subtract S, which is the semi-perimeter, from subtract A and B and C from the semi-perimeter and use that as numbers that get as part of the polynomial. Okay? It turns out this gets a perfect answer. And so what our software does, the core engine, is a search algorithm that allows you to search through the possible parameter space to find the most robust features that answer a question. So the impact of that is that people don't have to do this by hand anymore, or they don't have to do as much of it by hand, which makes them much more productive, and it also opens up the technology and the discipline to people who it wouldn't have been accessible to in the past, which dramatically expands the number of people who can play in the game. So back to our demonstration. Hopefully it's done. It is done. So I'm thrilled to do this. This again is in public for the first time. I'm thrilled. So this is the equation that it generated, and you can see that we gave you 4 rows of the input data that it worked on, and 4 rows of the output data that it generated, including the features that it built. And there's still error in the result. There's about 0.006% MAPE. And the reason that there's still error is there's noise in the data. And if we went to 1 billion examples, the error would go down. We could run it again and only do 1,000 examples, and you'd see the error would go up. But it's still nearly 0. And the reason that we think that this is a huge advance in technology is, again, this is all happening from the machine. Instead of human beings doing the work, it's the computer computing it. So what happens when big data gets a lot easier? It opens up a variety of different things that can happen before. We can calculate pricing spreads in near real time. We can better estimate the risk associated with any transaction faster than ever before. You can better prioritize your salespeople based upon dynamics that are occurring in the market right now. These are the kinds of things that you get the capability to do that you didn't have yesterday. And so I personally am thrilled that I get to work on this. And I'm also grateful to my team to give all of us the opportunity to build this kind of technology and make it available not only to the financial services companies that we currently serve, but also in general the rest of the world. I mean, eventually we hope to work on personalized health problems and even bigger problems like how you build space stations. But to summarize here, let me thank you again for your time and attention. I know it's getting late in the evening. We think this is a major shift in how people will consume machine learning technology and big data technology in general. And I wanted to share it with you to get your feedback and also to hopefully work with you in the future. I spend about half my time in New York City now because a lot of our customers are located here. And I hope to get to know each and every one of you. Thank you.
That's terrific. Right, we probably have time for, I guess, one question, but you're obviously going to be here.
Sure.
Ben, this gentleman, whoever is closer to you.
Thank you. Nick Hartman from CCAM Advisors here in New York City. I just have a question about fitting the data to an algorithm or equation. I think something that data scientists learn very quickly is that correlation doesn't necessarily equal causality, and that there isn't necessarily always an equation that describes what's going on in the data, even though we sometimes try and fit that. So in the example you gave, there clearly was a underlying equation. You modeled what the equation was. I guess my question is, how within data do you determine, is there something to model in the first place, which I think is often the problem faced by data scientists. You can always make an equation or fit numbers to an equation, but how do you know that it matters in a particular context?
You're absolutely right. So let me just summarize the question back for the rest of you. I mean, the question is, how do you know how to drive our system? How do you know how to drive any machine learning or statistical analysis system? And is that a reasonable summary? Yeah. And there are two answers to that question. First, our team works with our customers to help them build and formulate problems that can be addressed. That's number one. Number two, the technology in general predicts goals. And so what we have to train all the people who work with our system, regardless of whether they're data scientists or not, is how to express a goal. And so an example, in this case, the goal is to predict the area of the triangle. On Wall Street, one of the things that we might predict is the estimated spread for a trade position. Okay? Another thing that you might predict is the estimated price of a stock, of a commodities future. Okay? And so the way that you control the system as a data scientist is that you structure you basically structure an experiment where the experiment can, as an example, perform a back test that estimates how effective you are at estimating the thing that you're trying to estimate. And so in the background, from the script that I showed you, the system is actually doing that using defaults for the system for this problem. And what's actually happening is that it's breaking up all of the 100 million triangles into three groups. One is called a training group, another is called a tuning group, and a third is called a testing group. And in the first group, the training group, which in this case represents about 75% of the data, it's actually analyzing the patterns to see how well it can understand them. And in the tuning group, it's then it's using the estimators that it's built in the first pass to figure out, whether or not the predictions are right. And it's doing that, thousands upon thousands of times to figure out exactly which model might be the best candidate model. And then at the end, we actually use the test set to report performance. And so why do we do that? Well, as data scientists, we know that if we structure a problem like that, that we can get a fairly good estimate of whether or not the system is actually learning. If the system does not, if the system goes what's called sublinear in its learning capabilities, if the estimates on the test set are lower than the estimates on the tuning set, the system may not be learning effectively. And we would basically report that and say this problem is problematic. And so, by giving the user a few simple rules, one of which includes when it says that this is problematic, you don't base a $100 billion decision on it. You can help people make effective use of the technology. But it does require some training, you're absolutely right. And so we actually do not sell our technology as a complete replacement for data scientists. We encourage you to think of it as a huge productivity gain. And when I say huge, I mean it's an incredible productivity gain. If you think about, one way to think about our technology is that we took all of the methods that we used as data scientists that we collected over the last decade, and we embedded them in the system. And then when we hit a new problem, and then we made the system fast enough that when we hit a new problem, we could try all those methods. And once you tried them all, you'd essentially get some hints about what to do next. And you would, we taught the system how to do that. And over time, the system can learn the patterns in what works and what doesn't work. And so in answer to your question, the technology is not at the phase yet where it's completely automated and can be used by anyone. But it's certainly made a major generational leap over when I was training graduate students at Cornell only a few years ago. When we started to train graduate students, it was a huge amount of work that they had to do just to build basic machine learning systems or statistical analysis systems, and this is a huge step forward in that. Thank you for your question. Thank you for your time.
Thank you very much. Perfect job. Thank you.